Hello and welcome back to Dr. Logic Awkwardly Does Logic with a couple of anxious cats in the background. I think they're mad because I'm sitting in the chair that they like to sleep in when it's warm out. In any case, let's do some more proof examples using our predicate logic proofs. I've actually got two set up on the whiteboard already just to save the time of writing them down. So, on the one hand, we've got this proof with two premises. For every x, if ax, then bx, and for every x, if bx, then cx. And then from this, we will prove that for every x, ax, then cx. So if every a is b and every b is c, then every a is c. This is just the predicate's logic analog of Barbara. And then in the other one, we will prove that if for every x, ax implies bx, and m is not b, then there is something that is not A. In fact, it's going to be M. Spoiler, but we'll show this along the way. So let's start over here with this one. As always, we know how to begin. We write down our two premises that every A is a B, and that every B is a C. Now, let's look at what we want to prove. We want to prove something with a universal as the main connective. So we're going to have to use universal introduction somewhere down here. Maybe not that far down, who knows. In order to do universal introduction, we would need to have something of the form A implies CA, where A does not occur in any assumption that this line depends on. So right now, this is okay because we've only got these two assumptions and they don't depend on, they don't contain any constants. But this is kind of an interim goal that we know if we could get that, then if the provisos are met, we will be able to apply universal instantiation. So let's start with that. Let's see what happens if I try to derive this conditional. Now we are back in happy propositional land. So I start off by assuming the antecedent, and then our goal is to get CA for conditional introduction. Ugh, I can write a better scope line than that. Let's try that again. There we go. Now, remember what I said in the previous video. Anytime that you've got universal statements and you have a constant, immediately, without thought, reflexively, just do universal elimination on that constant. So if we look at the first one, this one says for all x, ax implies bx. So universal elimination would get rid of the quantifier and then replace a for every free occurrence of x. So that gets us AA implies BA. So universal elimination on line 1. Similar process for line 2. That one gets us that BA implies CA. So universal elimination line 2. Now, again, since we're back in happy propositional land, there's loads of things that we can do. You might first see 3 and 4 and say, aha, I have a conditional and its antecedent. Why don't I do conditional elimination? Or you might see 4 and 5 and say, aha, I can do, and we'll just go ahead and do that, conditional, sorry, not conditional. So this is the transitivity of the implication. So one of our derived rules from propositional logic, not to be confused with the transitivity of identity. There's just too many transitive relations out there. Now you might think, ooh, look at that. That was the conclusion. This is the conditional I'm trying to get. But we can't just pull line 6 outside of the scope line and get it to where we need it to be. There isn't a rule that would allow us to do that. So in fact, what we need to do is say, okay, I do still have to do the conditional elimination in order to get CA. So we've got that AA implies CA in line 6. We know that AA is true. So now we can do our conditional elimination, lines 3 and 6, and we get what we want. And that allows us to introduce that same conditional again, that AA implies CA through conditional introduction, lines 3 to 7. Now, we did this so that we would get something that looks like this, which we did, so that we could apply universal instantiation. So what we need to check before we do that is, does A, the constant that we're going to be generalizing on, occur in any of the assumptions that line 8 depends on? You go up, lines 1 and 2, no constants. The fact that A occurs in line 3 is not relevant because line 8 does not depend on line 3. So we have met our provisos. We can do universal introduction on line 8, and that is what we wanted to prove. Hurrah! So let's look at our second example. Start off by writing down our premises. This one says every A is B. And then we have something here that says, well, M, some particular object, is not B. And from this, we want to prove that something is not A. Now, there are a number of different kind of things that you could do, but I really encourage you to, at this point, stop and think about what your premises and conclusion are saying. Because if you can kind of see why the conclusion needs to be true, if the premises are true, this will make it easier for you to kind of pick out what would be the method for actually proving it. So we've got this constant M in line 2. What's the reflexive thing that you should always do if you see a constant and a universal statement? Universal elimination. You know that AM implies BM. Now we are looking for something that involves the negation of some A claim. And we want to be able to get not A something so that we can do existential introduction on it. But looking at what we have here, we know that if M is A, then it is B. But we know that it's not B. By propositional reasoning, modus tollens on lines 2 and 3 tells us that it's not going to be A. So M is not B, therefore it is not A. Then, existential introduction allows us to take any sentence that we have, take any term that we have, oops, that's not the way to write it, and replace that term with a variable that is then quantified over by the existential. Existential introduction, line 4, gets us that there is something that is not A. So this is exactly the same step that we did at the very end of the second proof in the previous video, which I just did for the fun of it to give you an example, but hey, look, here you have another example. Next time, we will look at some proofs that involve existential elimination. We might do just one proof for that video because it might end up being long. This is the one where you need to kind of check all of these different things, make sure that tau does occur in one assumption, but not in any of the other assumptions and not in the thing that you are trying to do. I may try to give you some examples of proofs where proofs involving steps that I see people make wrongly on a regular basis. So I can kind of flag those up and say, if you find yourself doing this, stop, because that's not right. But we'll leave existential elimination for the next video because it's fairly complicated. Until then, take care. Cheers.